Okay, so the recording started. Welcome and good morning. Welcome to CSS321. This is lecture number 10. And in this lecture, we will talk about the Turing machine, which is another computational model that we will look at. And it will be the last one that we will look at in this course. Okay, so far we saw finite automata, we saw the push-down automata, and now we are moving on to the Turing machine, okay, which is considered to be the most complex computational model among the three. Okay, so actually, the progress that we make so far, we work our way up from the simplest automata, which is the finite automata, and then to the slightly more complex one, the push-down automata, and now we are moving on to the most complex one, which is the Turing machine. Okay, so uh, but um, but when you see when we talk about it, you will see later that the format, the pattern of it, is actually similar to the one you see before. Okay, except that there are some extra features that are added to the machine. Okay, and because these extra features, it gives the Turing machine like what we call like make it become more powerful than others. Okay, and here when we say powerful, we are talking about the expression power in terms of the uh, kind of the strings and languages that they can describe or explain. Okay, so uh, as you can as you can guess, the Turing machine at the end of the day will be similar to the automata in some finite automata in some sense, but also with some extra feature, just like what we did with the push down automata. Okay, so before we dive into the content, okay, there is a announcement first, okay, about the final exam. Okay, so the final exam, okay, the final exam for this course will be on the December 3rd. Okay, so which is, what is it? Friday. Okay, so it is Friday, December 3rd. Okay, and what else? Let me see what else you need to know. Okay, so the format of the final exam will contain like 5 sections. Okay, where each section um will have 20 marks. Okay, um so in order to get you familiar with the format of the exam, okay, there is a practice, the final practice exam that you can look at, okay, which I posted on the Google Classroom. Okay, so if you go to the Google Classroom, go to classwork, okay, now you should see the final exam practice. Okay, and in there, it contains the exam from the previous year, I believe, or maybe just some questions. Okay, just to give you the idea what kind of questions will appear on the final exams. Okay, but so this is like from previous years where we have the exam on site in the exam room. Okay, but this year, due to the COVID-19 situation, we will conduct the final exam online on Google Form, just like in the midterm, I believe. Let me check quickly. Da, 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 da. Okay. Da, da, da. Okay. I believe it will be conducted online through the Google Class through the Google Form, right? Last time the exam was on the Google Form. Okay, it will be the same for the final exam. Okay, so and also the protocol that you need to follow will be the same or similar as well. Okay, so um, okay, so that will be the what else? Oh, okay, so about the final exams, this is the kind of questions that you can expect to see in the final exam. Okay, it will be something follow this line. Okay, so this is guideline of what kind of questions you might see in the final exams. Okay, so you can use this material to help you prepare for the uh, helps you get familiar with the kind of questions that you will see in the final exams. Okay, so you can take a look at it. Okay, so it has like of three of them. Okay, so it's like a three practice exam that you can look at. Okay, so okay, so it also tells you like the material that will be on the exam as well, which mainly include what you see here: set theory, start from set theory, go to the regular language and finite automata. Okay, and then we to the context-free language and push down automata, and then also the Turing machines. Okay, so mainly the content will the content in the final exams will cover these topics. Okay, so that should be it. Okay. Okay, so that's it about the announcement about the final exam. Okay, the exact time I don't know yet. Okay, you can check with Kunan in order to confirm about the time. Okay, but right now what I know is that the final exam will be on the uh, December 3rd. Okay, which is what is it? It's like 3 weeks away, isn't it? 1, 2, 3. Yeah, 3 weeks. Next 3 weeks. Okay, so any questions about the final exams? Okay, if not, then let's move on to our content today. Okay, so let's start. Okay, so what will we cover in this lecture? Okay, so this lecture mainly will give you like a introduction to Turing machine. Okay, so obviously that's why we will start with the definition and what it look like. Okay, and then next we will talk about the configuration of Turing machine. Uh, okay, which is the configuration here, just like telling the uh, it indicating the status of the current machine and also the environment around it, including the input string or the remaining of it, and also uh, the content in the memory. Okay, so that is what the configuration will tell us, just similar to the push down automata. Okay, and then at the end, we will look at the concept of combining machines. What does it mean? Okay, so it turns out that the Turing machines, okay, despite its capability to do many things, and to the point that is very similar to the conventional computer with think of it like an old computer with like a one core, one processor and memory. Okay, so the Turing machine is similar to that. Okay, and it turns out that although it has many features and can do a lot of things, okay, but in order to complete a task, okay, it can get very complex very quickly. Okay, so it turns so the alternative way to achieve this is just like how we do in coding. We break it down. Okay, we break the code down into a modularization, right? Where we break the piece of code into a functions and call it and create a functions that basically group the piece of code that try to achieve that basically as a collection try to achieve some kind of subtask. Okay, so this is the same idea that we would do here in the combining machines too, where we will break down, or you can think of it like that. You can break down the Turing machine from the big one into the some smaller pieces. Okay, where you uh, plug it together into the bigger machines. Okay, so that is one thing that we can do, or I mean, it's a concept that we will do in Turing machine. Okay, because the Turing machines can, I mean um, the diagram of the Turing machine can get very complex very quickly. Okay, so that is why we prefer this in order to be able to um, still understand what is going on in Turing machine. Okay, so that is what we will cover in today's lecture. Okay, so let's start. Okay, let's start from the Turing machine. Okay, so okay, so here okay, just a quick fact about the history. Okay, so at some point in the history when we just create the computer, okay, there is a question about this, about the feasibility of the computers, or you can call it the computing machine. Okay, so we want to know like the limit, the feasibility, what kind of questions that the computers can answer or can compute and find the answers. Okay, we want to be able to define the set of problems that the computers can solve. Okay, and obviously, in order to do that, the what the scientists like to do is to use math. Okay, to use math to show this. Okay, with math we know how to prove like the boundary or the limit of things. Okay, that is why in order to show the feasibility of the computers, we need the formal model of the computations. Okay, so we can describe the computers in terms of mathematics, and then from mathematics point of view, then we can prove the limit of the computers. Okay, and that is where the Turing machine comes in. Okay, so the Turing machine is considered to be a standard automaton of the computer, in general. Okay, so here when we say computer, as I said, is from the is a history. Okay, it's something that happened a long time ago. So at that point of time, the computer usually contain only like a one CPU or one processing unit, and then maybe a collect, and then a memory. Okay, basically just like a two. You can think of it as a two main component there. Okay, that is I mean only the CPU and the memory are the main components that involve in the computations. Okay, and here we are not including, here we just ignore the IO, the input output equipment. Okay, we just kind of assume that the input is already is already read and be pass it down to the memory or the processing unit already, and also the um, output would be the what the machine tells. Okay, what the CPU can determine. Okay, so we can ignore it and focus only on the processing unit and the memory. Okay, and the Turing machine is a kind of the computational model that does this. Okay, and the name is comes from the Alan Turing, a person who invented this, and we call him the father of computer science. Okay, so that's just a fun fact. Okay, so now let's move on. What do we want? How do we design the Turing machine? Okay, in order to describe the conventional computer. Okay, so again, just to clarify, the conventional computers here that we talk about is not like the computer that we have here in front of us that have like multiple core and multiple threads and be able to compute and process things in parallel, and also with a different kinds of memory that the computer can take advantage of. Okay, when I say the computational the sorry when I say the conventional computer here, we are talking about the old one from like 20 or 30 years, actually 30 or 40 years ago, where we have only like a one CPU and maybe one chunk of memory, and that's pretty much it. Okay, so that is what we are talking about here. Okay, but anyway, even the modern computers, okay, is still uh, how do you say that, based on the same concept as the conventional one. Okay, but with obviously multiple features being added. Okay, so let's look at the Turing machines when when he decided. Okay, when we did, when he decided he wanted to satisfy these three criteria. Okay, so mainly, first, the Turing machine, they wanted to still be an automata. Okay, so what does it mean? It means that the design of the Turing machine, okay, it must still share some general spirit as the previous computational models that we saw earlier. Okay, so what it means by this first bullet point is that um, the Turing machine, okay, when we design it or describe it, it should be similar to the other automata, like finite automata or push down automata. Okay, and that is how they designed it. Okay, and the reason for this is also similar to previous one as well, since we know how to prove the previous using the previous computational model to prove many things. Okay, so if we follow the same pattern or follow the same or similar definition, then we should be able to do this similar things as we did in previous automata as well. Okay, so that is the idea. Okay, so that is the first point that they take into account in designing the Turing machine. Okay, second, they want the machine to be as simple as possible while be able to describe or while in the third bullet point be able to um, describe the actions or the computations that the computers can carry out. Okay, so think of it. This um, the two main design rationale is number 2 and 3. Okay, so number 3, they still want this Turing machine to be able to describe the capability of the computers, while number 2, they want this description or this computational model to be as simple as possible. Okay, and the number 1 is kind of how they achieve number 2. Okay, is that to make it as simple as possible, then what they do is try to describe it in the way that's similar to how they describe the previous computational model like finite automata and push down automata. Okay, and that is how they come up with these Turing machines. Okay, and why it looked like this rather than others. Okay, so that is like the background before we get to the main content. Okay, so now let's start looking at the Turing machine finally. Okay, so the Turing machine, okay, think of it as a finite automaton, but this time it is equipped with an infinite tape as its memory. Okay, so if you remember, for the finite automata, we don't have any kind of memory. Okay, the only kind of memory, which is not actually memory, is the state. Okay, in the finite automata, they use the state to as a kind of memory, not really memory, but use it to memorize the kind of input string that they have processed so far. Okay, but then in the push down automata, we equip it with the stack data structure as the memory, and as you see or as you saw already, that with the stack as the memory, we can do more stuff with the push down automata compared to the finite one, to the finite automaton. Okay, and now in the Turing machine, we switch the stack memory with the infinite tape as its memories. Okay, so with this infinite tape, think of it like a RAM. Okay, the random access memory in the computer. Okay, since it is in okay, although the RAM is finite. Okay, but the idea here is that they make it infinite so that they can use it to prove how do they say that, to remove the constraint about the size of the tape or the memory out of it, so that when they prove it using math, it will be easier. Okay, so that is think of it as this Turing machine is describe the computer from the theoretical point of view. Okay, so that's why we can just kind of assume that the tape or the memory is infinite, although in reality that cannot be true. Okay, so anyway, so the Turing machine now, it is the finite automata with the infinite tape as its memories, that and then what else? And then this tape, okay, as I mentioned earlier, we assume that the input here, we don't want to focus ourselves on the input and output procedure. Okay, so that is why we assume that the input is already read and written on the tape or the memory already. Okay, and then we just assume that the art part of the memory that haven't been used by the machine, they just contain blank cells. Okay, and it just means that it is ready to be used. If we want to store something, we can put the information there, okay, and use it later. Okay, what else? And then the Turing machine also has a tape head that you can use it, and this is the main way, and is the only way that you can access the memory. Okay, and with the tape head, you can read or write, um, read or write into the memory. Okay, but here there's a constraint that you can only write or read a single cell at a time. Okay, you cannot just read the whole thing up, or write everything down. Okay, actually, it is very similar to the conventional computers, right? In the RAM, computers can read one item at a time as well. Okay, but with the how do you say that, like optimization, they might try to make it read like a chunk of memory and so on to faster the process. Okay, but the general idea is the similar in the sense that you can read like a one, okay, not cell, maybe, and let's say it like an one item at a time. Okay, whatever that item would be. Okay, so that is what the Turing machine is about. Okay, now here is the picture that may give you a better idea about what it looks like. Okay, so Okay, as it said earlier, the Turing machine is a finite automaton with the infinite length tape. Okay, so here's the tape. Okay, and here's the automaton where you have state and all these transition relations that tells you how the state would transition from one to another and so on. Okay, while the infinite tape here act as a memory that you can store the intermediate result, or and also at the beginning we assume that the input string is already stored in here. Okay. Okay, so what else? Hmm. Okay, so in the Turing machine, okay. Oh, okay. Here, just one more comment. Okay, so here in this lecture, okay, we will use this convention where, in the infinite tape we have this symbol, this triangle symbol here. It shows that it is the start of the tape. Okay, and all the input will be put next to it, basically. Okay, so it will start with this symbol to tell you that this is the at the beginning of the tape, and then the following will be the input string. Okay, so this is the convention that we will use. Okay, but if you read other textbook, what you might see is that they might not use this symbol, and they just assume that the tape is infinite in both directions. Okay, here we just assume that the only right side is infinite. It just keep going on forever. Okay, but on the left side it start from this symbol. This symbol tell us that this is the leftmost cell of the tape. Okay, but in other textbook they might say that it is infinite in both way. So either way is fine. Okay, but with this convention, me personally find it easier to understand what is going on with the Turing machine. And plus, it looks more like a reality where if you think of it as a tape, you cannot, I mean, it should start somewhere, right? Like, think of it like when you insert a tape into the computers, or make the computer reads the information from the tape. Okay, it should start from somewhere, right? So that is why, in my opinion, I think that this convention is easier to understand. Okay, and that is why we will stick to it in this lecture. Okay, but here I just comment to let you know that if you see other variation, okay, don't panic. It is the same. I mean, the same. The general concept is the same. Okay, but the details of the definition might be slightly different, but the general concept will be exactly the same. Okay, so okay, now let's look at the component of the Turing machines. Okay, the Turing machine consists of three parts. Okay, it contains the finite state control, okay, which is just like the previous automaton that we saw before already. Okay, which contain the state, and it contains the state, the um, and also like the transition relation and so on, so that we know how to transition from one state to another when we see the given input. Okay, that is the first component. The second component is the infinite tape that you can store the input and also the intermediate result that if you need it. Okay, and the last part is the tape head, which is the equipment that allows you to interact, allow the finite state control to interact with the infinite tape. Okay, and here is the limitation where we can read and write a single tape cell one at a time. Okay, so this is the three components of the Turing machines. Next, we will look at what the Turing machines can do. Okay, so this is in each step. Okay, this is what the Turing machines can do. It either write a symbol to the tape cell at the position where the tape head is, or and also change the state. Okay, in the finite state control, you can change the state, and Oh, okay. So actually, the change the state can be done all the time. Okay, but the first one, the third one, it is an option. Okay, you can either write the symbol to the tape at the location where the tape head is, or you can move the tape head to the left or to the right location from the current one. Okay, and then you can change the state in the finite state control. Okay, so that is basically the everything you can do with the Turing machines. Okay, so that's it. Okay, that is all you can do with the Turing machines. Okay, so now let's move on to look at the formal definition of the Turing machine. Okay, the formal definition of the Turing machine can be described by these five tuples. Okay, by this five item tuple. Okay, where the first item is k. It indicates a finite set of states. Okay, so this is similar to what we see in other automaton, and the same go for sigma, which is an alphabet. Okay, but this time our alphabet not just the all possible symbol in the input, but it also include the okay, it also include the blank symbol, which indicate the blank cell in the infinite tape, and also the left end symbol, this triangle that I said talk about earlier, that it indicate the beginning of the infinite tape. And oh wait, actually that's it. Two more symbols are added to the alphabet. Okay, but and for this arrow symbol, we will see it later. In the arrow symbol, just indicate that we want to move um, the tape head to the right or to the left according to the arrow. Okay, but these two symbols are not in the alphabet. The alphabet is just all the possible string symbol, the input symbol, and plus the blank symbol and also the left end symbol. Okay, that's it. That is our sigma. And then next, okay, let's look at S first, which tell us what state is the initial state. And what else? And then the this one H is the set of halting states. Okay, so here is the another difference in the Turing machines. Okay, so instead of the final, normally we will say we will have the final states, isn't it? But this time in the Turing machine, we will have the halting states. Okay, we will see later what is the difference. Okay, we will see the difference later, but it is still share the same general idea where the halting state is where if our Turing machine reach this state, okay, then it will stop the operation basically. Okay, we will see later what the difference is. Okay, now let's look at the last component, and you can think of it as the maybe the most confusing one, the transition function. Okay, so this time it is okay. It is a transition function right now. Okay, so here we are talking about the deterministic Turing machine right now, where we know exactly if we see the input, we see the state, then we know exactly what to do. Okay, so what else? Okay, so here that's why we call it transition function again, not the relation. Okay, because there's only one possible outcome for any combination. Okay, and this time it is a function from this k minus h, okay, multiplied by the sigma. What does it mean? It means that it is defined over all states that are non-halting states. Okay, um, we define this transition function for all states except for the halting states. Okay, and then we define it for every possible alphabet possible that we might see in the input. Okay, so what else? And then it will map us to this. Okay, it will be a pair of the next state and the symbol. Okay, and the symbol given over here. Okay, which is can be the alphabet or the left or right arrows. Okay, so here there are two cases possible. If it is the alphabet, okay, the sigma, then we just write it down at the current location of the tab head. Okay, that is what we do if we got this as from the transition function. But if we get the arrows, what we do instead is we move the tab head. Okay, so if we got the alphabet, we don't move the tab head. We just write the this symbol down into the tab. Okay, but if we see the arrows, we move the tab head. Okay, and to the location, to the direction according to the arrow. Okay, what else? Okay, so here are some transitions that must be included in all transition function of the Turing machine. Okay, so sometimes we would just omit it because it is obvious that they must be added already. Okay, so what are they? Okay, so the first one is about the when we see the input, when we read the input tape and we got this, the left end symbol. Okay, so that's why we have this transition function for every state, except for the halting state. Okay, if we are in the non-halting state and we see the left end symbol as the next input, then what you do, you just move to the right of it. Okay, basically just move away from the left end symbol. Okay, and move on to the next cell. Okay, which there's only one, and which is the cell on its right. Okay, and that is what happened here. Okay, and of course, the state, if you're in this state, you can transition to another state or stay the same, whatever. Okay, and it should be included in the transition function. Okay, and the next kind of transition that must be included in the transition function is okay, in is this. Okay, so here the second one here they're talking about the transition in general, where if you see the symbol, as I said earlier, if you see the symbol, the alphabet, then you just write it down at the tab head. But if you see the arrows, you just move the tab head. That's it. Okay, so this is what the Turing machines look like in terms of the definition. Okay, okay, we will see the example later. Okay, and that way it should make it easier to understand what is going on here. But anyway, let's move on. Okay, so here are some. Oh, actually, I described here already, isn't it? Okay, so here, as I said earlier, that the infinite tape, in some textbook, it might mention that the infinite tape go both ways, left and right. Okay, but here in this lecture, we will use this convention where we assume that the leftmost end of the tape is marked by this left end symbol, and it's not infinite to the left direction. Okay, it's only infinite if you keep moving to the right. Okay, and okay, so here and this symbol help us prevent the machine from moving the head of the tape, basically. Okay, and okay, and basically this first group of this transition, it basically what it does is preventing the Turing machines from moving its heads off the tape. Okay, and that is why when the head reads the left end symbol, it must immediately move to the right in order to avoid going over the tape. Um, Okay, and here we will use the arrow symbols left and right to denote the movement of the tape head. Okay, and these two symbols, the arrows, are not members of the alphabet. Okay, these arrows are not part of the alphabet. It only exists in the transition function as the output as well. Okay, you can only see it as the output of the transition function. That's it. Okay, so what else? So here at the beginning, okay, just to state this again, that at the beginning, the Turing machine will begin with the infinite tape of the blank cells, okay, where the input will be written on the tape at the beginning already, okay, um, and it will be put immediately on the right of this left end symbol. Okay, and okay. Here I put the mention here that in the other versions, which mean the one that with infinite tab in both directions. Okay, the input can be written in some location anywhere. Okay, what else? And then we in this convention we assume that the tab head is started uh, at the first symbol of the input. Okay, or you can assume that it start at the left end symbol is fine as well. Is the same. Okay, and then what else? And here the limitation that we mentioned earlier that the Turing machine can only move its head one cell at a time. Okay, and it can also read and write one cell at a time as well. Okay, and then what else? Oh, the last thing about the halting state is this. Okay, so this is how the Turing machine ends, or we know that it finished its computation. So when the state reached the halting state, it the operation, the Turing machine stop in immediately. Okay, that is how it works in the Turing machine. Normally, in the final automata, in the push down automata, we need to finish processing the string and finish at the final state. Okay, that is how the final state works. Okay, but this time we have the halting state, and how it works is that if you reach this state, then it just finish the operation right away. You don't need to finish processing the whole string or remove everything from the memory to in order to stop the operation. Okay, but however, after we halt the Turing machine, we have to look at the final state and other conditions as well before we can tell that the Turing machine accept the string or not. Okay, we will look at that later when we talk about the configuration. Okay, but right now, what I want to mention is that they use the halting state, and if we reach it, we just stop the Turing machine right away. Okay, and that is why the transition function is not defined over the halting states, because when we reach it, we just finish, we just done, no more, we stop the Turing machine. Okay, so there is no need to define on them. Okay, so okay, that's the example. Okay, let's look at the example and what does this Turing machines look like. Okay, and what is it? Okay, so here is the Turing machine for accepting this string. Okay, where the length of this input is even. Okay, and that we want to build the Turing machine to accept this language. Okay, so let's define our Turing machine M, which composed of these 5 components, and let's start. Okay, so start from K. Okay, so the number of states, what do we have? So here we will have in total 5 states. Okay, we have the S as the start initial state. We have Q0 and 1 as the intermediate states. And then we have Y and N as the halting state. Okay, as you can see here in H. Okay, the H, you see that halting state including state Y and N. Okay, which we would indicate later that Y means that we accept that string and N if we don't accept that string. Okay, next what we need to define the alphabet sigma. Okay, so here the only alphabets that we have is A and B. Okay, but this alphabet also include the empty string, the empty, not empty string, I talk about the empty cell. Okay, and also the left end symbol. Okay, but here we would not include it. I mean, when we write it down, we will not actually include it in the sigma. I mean, we can include it or not. That is fine. Okay, if you're not, then it is by default that these symbols must be included no matter what. Okay, so we can just skip writing these two symbols. That's fine. Okay, what else? Okay, the S is will be the initial state, and then the last thing that we need to define is the transition function. Okay, and the transition function is given in this table. Okay, okay, so let's look at this transition function table. What does it tell us? Okay, let's get us familiar with the transition function first before we start looking at the input and how they process the string. Okay, let's look at the first line. What does it mean? Okay, so the first line, what it tells us is this. Let's say that we are at the current state is S, and the next input that the machine reads is a blank cell. Okay, and what happened is this will be the result. The result is that the next transition will be Q0, and at the same time it will move the location of the head to the right. Okay, it will move to the right because you see the right arrow there. Okay, and on the other hand, if you are in the state Q0 and the next input string is blank cell, then what happens is the next state will be Y, and the blank cell will be written back into the memory. Okay, and actually this thing can be it can write anything back to the memory because we reach the halting state, so it doesn't matter anymore. Okay, the operation of the Turing machine will stop when we reach this state. Okay, so what else? Um, okay, so that should be it. Okay, so hopefully you should get the idea of how the transition function works here. Okay, so now let's move on to see some example of how this string machine process a string. Okay, so let's see. Okay, so first let's look at this first one. It is a string of AA. Okay, very short. Okay, let's look at the simple string first. So it is AA. Okay, so here just to clarify in the finite automata, okay, the finite tape will look like this, okay, where you have the left end symbol and then you have the um okay, so here we also include like a blank as well. Let's say it's a blank and then AA. Okay, so that's why we have blank AA. Okay, so blank is also part of the input. Okay, so that's why we also include it. Okay, and then what next? Okay, and then next, as I mentioned earlier, okay, we will start from the first location of the input. Let's say that our head, the tape head is over here already. Okay, I mean, as I mentioned earlier, you can start from here, but with the transition function, it will just tell us to move to the right. So it will be in this location. Anyway, so um, okay, so that is what happens. Okay, so now we are in state S. Okay, so the current state will be S, would be S. Okay, next, what happened next? Okay, so now we are in state S. We see the blank cell. We basically looking at this rules. Okay, and what happened is we convert this current state to Q0, and we move our tape head to the right. And there you go. That what happened in the first transition. Okay, and then the second transition, what happens? We are in Q0 and the input is A, so here we go. We use this transition function. We switch from Q0 to Q1, and again, we move the tip head to the right. So now we are at this location. Okay, now what happened? We are in Q1 and we see the input string A. Input symbol is A. So what happened is we switch back to Q0 and we move our tape head to the right. So now we reach this point where we assume that it has the blank cell over there. Okay, then what else? And then we are in Q0, we see the blank cell. Then what happened is this. We just switch the state to Y and we read this symbol and then we write the blank cell back to the same location. Okay, so nothing changed. The tape head location is still the same, and now we are in the halting state, and that is it. The Turing machine terminates because we reach the halting state, and that's it. Done. Okay, so that is how it works. Okay, so this is for the first this string. Okay, now let's move on to look at the another example, which is space A. Okay, so let's rewrite this. Okay, so here we are moving on to look at this one. Okay, let's look at this one. Look at the second example. Okay, the current state would be S, and now the current tab is looking at this. Okay, what happened? Okay, so first we use this first rule. We switch this to Q0. The current tape head go to this location A, and then from Q0A we change to Q1. Okay, and then move the tape head to the right, which this part is the blank cell. Okay, we kind of assume that it's a blank cell all over the place. Okay, but we don't have to write it all down. Okay, when we are in Q1, we see the blank tape, blank cell. What happened is we switched the state to N, and we just write the blank cell back into the same location, and we don't move the tape head. Okay, and since we reached the halting state and the Turing machine terminates, and in this case, we interpret the halting state N as reject the string. Okay, so that's why this machine reject this string, and that's it. Okay, so now you see how the example of the Turing machines and how it processed the string already. Okay, so to this point, any questions? Any questions so far? Okay, so if not, okay, let's look at one more example of how you use the Turing machine. Okay, let's look at it one more time. Okay, so this time we have these Turing machines. Okay, so this one is a different Turing machines. This time it has only three possible states: Q0, Q1, and H. And the initial state is Q0, and the halting state is H. Okay, and the alphabet is only has A, and also the blank cell and the left end symbol. And what else? Okay, and here this table show us the transition table, the transition function. Okay, so now let's look at this. What does it? Oops, what's wrong? Give me a second. Okay, so okay, so let's look at one at a time. Okay, so let's look at this one. What happens to this one, or what will happen to this one? Okay, let's start from the drawing down the tape. Okay, this is what will happen. We will have the left hand symbol no matter what, and then all the input will be written on the right of this symbol, and then after it finished, the remaining of the cell will be filled with blank cell, but we don't need to write all of that down. We just assume that it just go infinitely. Okay, so what else? Okay, the current state. What is the current state? Okay, the current state, okay, at the beginning, it will be Q0. There you go. Okay, now let's start. Okay, let's begin our tape head over here. Okay, since if it start from the left end symbol, we just go to this location anyway. Okay, anyway, let's start. Okay, first we see the current state is Q0, the input symbol is A. What happened is we just switch this to Q1 and we write the blank symbol, the blank cell back into the same location. So that's why we just overwrite the input A, okay, and replace it with a blank cell. Okay, and then next, what happens? We see Q1, we see the blank cell. We basically just switch back to Q0 and move to the right. Okay, and what else? And actually, it's the same thing, isn't it? Switch back to Q1, blank cell, and then go this rule again. Q1 with blank cell, we just move to the right, switch to state Q0, go to the right, and then again, oh my god, how many times do I need to repeat this? Okay, this is torturing. Okay, blank cell, and then from Q1 blank cell we move to the right, back to Q0. Okay, this why we see again, and then we use this one again. Q0 and input A. What you get is state Q1 and blank cell over here. Okay, and then what else? And then we back to this uh this uh this transition. When we have Q1, we see blank cell, we move to the right and we switch the transition to Q0. Okay, now finally we got to this. We got to this transition where we see Q1 and blank. Oh, sorry, we see Q0 and we see the blank cell, and we just transition to halt state edge and write the blank cell back, which is the same, so nothing changed. Okay, so that's it, done. Okay, so we end up in the halting state, and here in this case, if we reach the halting state, we just say that we accept that string. Okay. So normally, by default, if it's not indicating anywhere, then we will just assume that if the machine reached the halting state, then it just accept that string. Okay, that is how it works for the Turing machine. Okay, but if it is specified otherwise, like you saw in the earlier example, then you know when to reject or accept the string based on the halting state that you reach. And what else? Here, let's look at another example, isn't it? Okay, another example. Here we have a Turing machine where we have only two states. Okay, the number state is decreasing, isn't it? Okay, and what else? And then the alphabet is the same. The starting state is Q0, which is the same, and also the halting state is the same, which is a set of edge. Okay, now this time we want to see that this Turing machine accept this string or not. Okay, so same thing again. Let's write this down on our infinite tape. Okay. Okay, so here our tape head start from here, the current location, the current state. The current state is Q0, which is the initial one. Okay, let's start. What happened? First, we use this one Q. We have the Q0 and we have the input symbol A. The current state Q0, input symbol A. What happened is, what is this? Oh, we just go to Q. We stay in Q0 and we move our tape head to the left. There you go. Then what happened next? What happened next is that we have the current state Q0 and we see the left end symbol, so we just move to the right. We move the tape head to the right, and then what else? And then what happened next is this. You see A, and then you just move the tape head to the left again. I mean, staying. You still stay in the Q0 state and so on. Okay, so as you can see, it will just alternate between these two rules, isn't it? And you just go between these two locations, and it basically just move the tape head back and forth forever. Okay, so what do you see here? It is an infinite loop, isn't it? We stuck in an infinite loop. Okay, so in the Turing machine, as you can see here, we can create a machine that basically can stuck in an infinite loop. Just like how we do coding. We can create an infinite loop in our code and break our code, isn't it? Okay, so that's um, and that is what the Turing machine is trying to do, right? It's trying to imitate the computer. Okay, so it basically trying to imitate what you can do in the computer. Whatever you can do in the computer language, you should be able to do in the Turing machine. That is the design rationale at the beginning, right? And that is this is part of it. Okay, so in the Turing machine, you can have the infinite loop. Okay, and then this is the example of it. Okay, so here just one comment. The operation of a Turing machine may never stop because it may stuck in an infinite loop. Okay, so that is what can happen. Okay, so I think that's okay. That is okay. Here to summarize about the Turing machine. So here I just want to point out the difference between the Turing machine and the finite automata. Okay, so that you get the idea of what is going on and what the difference between these machines. Okay, as you will see earlier, okay, the definitions, the tuples, they are designed in a very similar way to the finite automata. Okay, but here I want to emphasize the difference so that we see or we notice the extra features that are added here to the Turing machine. Okay, that the finite automata doesn't have. Okay, so what else? Okay, so what are the difference or the main difference at least? Okay, the first main difference is this. The Turing machine, oh, what happened here? Oops, what's wrong with you? Okay, the first difference is this. A Turing machine can both write on the tape or read from it. Okay, so basically it has the memory. Okay, it has the memory where the finite automata doesn't. Okay, or even the push down automata. Okay, the difference from the push down automata is that oh wait, no, never mind. Okay, in the push down automata we can write and read from the stack, isn't it? Okay, never mind. Okay, so here we focus on the finite automata. Okay, the Turing machine we can read and write to the tape or read from the tape. Okay, but only at the location of the tape head. Okay, and then second, the second thing that we can do, okay, is that we can move this tape head to the left or to the right. Okay, one cell at a time. And the second one, and the third one, that is that this memory tape that we have is infinite. Okay, so we can keep just writing things down into it. Okay, so even though the input string is infinite, we can still be able to handle it. That is what it means here. Okay, what else? The spatial state of rejecting and accepting state take effect immediately. Okay, so here we are talking about the halting state. This is the main difference that you should notice as well. Apart from the fact that Turing machine also have the infinite uh, tape as the memory. Okay, the other main difference is this about the halting state. Okay, this is what we this fourth bullet point is talking about it. The special state or the halting state, okay, which are there for rejecting or accepting the input string. They take effect immediately as soon as you reach those states. Okay, so when you get to those states, you just uh, terminate your Turing machine and see that and check that that special state or halting state are considered to be accepting or rejecting the input string. That's it. Okay, so that is how you determine whether the Turing machines accept or reject the given input. Okay. Okay, and again, here to emphasize one more time is that if the no, how to say that, if they are not defined that which state are for rejecting or accepting, then by default we just assume that if the Turing machine terminates, we just assume that they will accept that string. Okay. Okay, that's it. Okay, that is the basic about the Turing machine. Okay, so next we will talk about their configurations. Okay, but I think this is actually a good place to take a break actually. Okay, so okay, actually let's take a break. Okay, so right now it's like 10:11. Okay, let's continue at 10:25. Okay, so let's take like a 10 to 15 minutes break. Okay, we will continue at 10:25, and we will start looking at the configuration of the Turing machines, and then we will look at how can we combine these machines together to build a more complex system. Okay, so here the configuration would tell us how to describe the current state of the Turing machine. The current situation of the Turing machine. Okay, and then which we will be able to use it to describe the um, the machines and how they combine them later. Okay, so let's stop here. We will continue after the break. We will continue at 10:25. Okay. Okay, so see you after the break. Okay, so are you ready to continue? Okay, any questions from the first part or the content that we talked about already? Okay, no questions, right? Okay, let us continue then. Okay, so okay, so in the first half of the lecture, we talk about the Turing machine already. Okay, so we look at the formal definitions of the Turing machines and also see a few examples. And mainly what we see is that the Turing machine is basically a finite automaton with the infinite um, tape as a memory. Okay, and also how we terminate the Turing machine is slightly different from others automaton that we've seen so far, where we use the halting state. Okay, if we reach one of the halting state, then we just terminate the Turing machine immediately. Okay, we don't need to wait until all the input, all process or um, all the symbols in the tape are removed or something like that. Okay, as soon as we reach the halting state, that's it. Okay, it means that the the machine is terminated. Okay, so next we'll start looking at the configuration. How can we describe the configuration of the Turing machine? Okay, so let's see. Okay, so in the Turing machines, when during the computation of the Turing machine, it changed the current state of the machine. It changed the tape content, and it also changed the head location. Okay, so here these are the three things that we need to keep track of. Okay, since the input string will be written on the tape already, so we just need to keep track of the content of the tape. Okay, while the oh, and that's it. Okay, and the state just need to keep track of the current state and the current location of the head. Okay, so there is no need to keep track of the input string since it is written on the tape content already. Okay, so keeping track of these three components, or these three items, and we will call them a configuration of the Turing machine. Okay, since this is the all the information we need to be able to describe what is the current situation of the Turing machine. Okay, that is why we can define a configuration using this. Okay, so first part here is our state. Okay, so here is our state. Okay, let me write it down. Okay, so here is our state. Okay, what else? And here is our, what is it? Oh, okay. So here, this is how we describe the current tape content and the current head location. Okay, so this we will break down the tape content into two pieces. Okay, so basically this whole thing will be the tape content. Uh, okay, but the idea is that this where we break the tape content into two pieces is where the current head location is. Okay, you can think of it like this. Okay, so that is how we will define a configuration. Okay, this is what I said earlier. So for the content of the tape, we decide to break it down into two pieces, okay, where the first part is the left-hand side of the current location, the current head location, okay, and also including the current symbol as well, isn't it? Left part. Yeah, okay, and including the symbol that being at the location of the head as well. while the second part, okay, it will contain only the content on the right of the head. Okay, and it could be empty. Okay, if the location of the head is at the last symbol, then the right hand side would be empty, right? Okay, so that is possible. But for the left part, that is not possible. Okay, we do not allow empty string for the left hand side. Okay, okay, the first part must not be empty. Okay, but the right hand side it can be. That's fine. Okay, what else? Oh, so here so here we want our configuration to be unique. What does it mean? It means that if we talk about this configuration, there should be only one way to describe it. Okay, but however, since we have the infinite tape, okay, which means that for the right hand side part, we can keep adding the blank cell into it. Okay, and that is what we say here, that we don't want such thing to happen. Okay, so that is why we add this condition that the second string, okay, cannot end with a blank, in order to avoid this situation where we have basically the same content, and then the second one is just basically the same content but with the extra blank symbol, and these two basically are the same, isn't it? It basically, these two give you the same configuration. Okay, and then we don't want that, so that's why we don't allow this kind of thing to happen where the second string must not end with a blank. Okay, because we can assume that there's a blank symbol go all over the place, isn't it? Just keep going forever. Okay, so the blank is not allowed to be at the end of the second string. There you go. Okay, so now let's see the example. Okay, so what does it look like? Okay, so here, let's say, okay, so here are some example. Okay, so, the, 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 okay, so here, just one more thing to comment is that the blank cannot be, um, on the, wait, what is it? Okay, so, for the, okay, so here's what it looks like. Okay, so let's see. Let's say for this one, the current state is Q. Okay, and the string in the tab looks like this. The string in the tab look like this. It basically A, B, A. Okay, and the current location. Oh, okay. Basically, I already draw it there. Why I draw it twice? Okay, let me remove this. Okay, and basically, this is what tab content look like. It basically, you put these two pieces together. Okay, and as you can see, the location of the current head would be at this part. Okay, at this location. Okay, which is A. I mean the first A in the string. Okay, there you go. Okay, the same goes for here. The current state is edge. Oh, wait, what is it? This should be edge though. Okay. So here the letter in the box just indicate the current state. Okay, so this should be H. Okay, not Q. What else? And then in the tab content, we got this. Which will be all the way here. This part will go this part. Okay, and we will use the last symbol of the left hand side as the current location, and that is why we get this one. And there you go. And the same goes for the last one here. Current state is Q. There you go. And then this part go to the whole thing, isn't it? Okay. And then that's why the empty, it's just empty. Okay. Okay, and what else? The E is empty string. Okay, and here we use the last symbol, the left-hand side, as our colon location, and that is why we got this. Okay, and we've got this one, and that's it. Okay, so okay, what else? So here, as you can see, for the left-hand side, we are allowed we allow the left-hand side to end with the blanks, with a blank. Okay, but for the right-hand side, we do not allow it. Okay, when it is empty, we just say empty. We don't say blank. Okay, we will never say blank. We will never put blank at the end of the right-hand side. Okay, and that's how it works. Okay, so that is how the configuration of the Turing machine is. Now, but let's look at this two configuration. Okay, are these two actually a configuration? No, it's not. And why is that? Okay, why is that? Okay, the first one, this one is not because here. Okay, this are not allowed. The right hand side must not end with a blank. The correct configuration would look something like this. And that's it. Okay, and um, the actual content would look something like this on the tape. B A A A and then B, and then the location is at here, and we are in state Q. There you go. Okay, so as you can see, either you put blank there or you don't, is the same. No difference to the Turing machine. Okay, and what about this one? What's wrong with this one? This one, it is missing what? It is missing the left end symbol. Okay, so the correct one should be this. Should be Q, left end symbol, blank, A followed by B, A, and there you go. And this is what it looked like on the content tape. A, A, B, A. Okay, different cell might look a different size due to my poor handwriting, but it should be the same size. Anyway, the location must be here. Okay, according to the configuration, it must be here. Okay, over there. Okay, but sometimes writing it like this is very not very difficult for human to understand. Not very difficult, but it's difficult. Okay, difficult than the next notation that I will introduce, which we will call it a simplified notation. Okay, for describing the tape content and also its position, the location of the head. Okay, the idea is this. Instead of breaking the content down into two pieces, we will still keep it together, but this time we will indicate the location by the underline. That's it. Okay, but here, so this is what it looked like. Okay, so previously we have this, right? Okay, let me show you, put it next to each other so you can compare it easily. Oops, where's it gone? Okay. Okay, let me put it next to each other so you can see it easily. What's the difference? Okay, so here it used to be like this. Now we convert it to this. Okay, so as you can see, basically we put the content together and we underscore where the current location of the head is. Okay, and the same go for here and same go for here. Okay, so uh, why don't we just use the simplified notation all the time? Okay, the reason is this. And the reason is that with the simplified notation, we cannot really describe it mathematically. Okay, so that is the problem. With the simplified notation, we cannot describe it using the set and its member. Okay, in the set, we don't have the notation of underscore and the underline and so on. Okay, okay, so that's why we cannot actually do that. But here we introduce this simplified notation just for, how do you say this? Just for the sake of writing it down for human to understand it better. Okay, so what does it mean? It means that every time we write with this simplified notation in terms of math, it will see it like this basically. Okay, so we just use this like a aliasing, okay, as a like a alias of the formal definition. Okay, so that is the configuration looks like. Okay, and what else? Okay, so here is a configuration of the current situation. Now we will start looking at how one configuration deal another. Okay, so here is what we talk about. It's the same thing that we talk about in finite automata and pushed automata. When we have the configuration, we want to be able to define how one configuration can deal another. Okay, and here we will do it the same thing here. Okay, so here for the Turing machine, it said this. It said that one configuration will yield another if and only if it has to follow one of these three cases only. That's it. Okay, so for the first one we are talking about when we just replacing the current cell with a new symbol. That's it. Okay, so that is why for in the first case, the omega 1 and omega 2 are basically the same. U1, U2 are the same as well. And the only difference is that A1 is removed or read by the Turing machine and replaced by A2. That's it. Okay, so hmm. Okay, so this is okay, so this is one kind of possible transition. Okay, for that one configuration can yield another. Okay, so this is the case where you just basically replacing the value where the tape head is. Okay, next, the second type or the second case that is possible for the configuration to yield another is when you move the tape head to the left. Okay, so in this case, what happened is when you move the tape head to the left, what you need is this. It means that your omega 1 or the left hand side of the tape head must be omega 2 and A2, so that when you move to the left, the location will be at the A2 instead. Okay, so but here for the U2, there are two cases possible. Okay, the case for the first case, the 2A here is when there are other symbols after the tape head. Okay, so that what happened is after you move to the left, then basically the current symbol will just be added to the right hand side, and that's it. Okay. And here on the second case, 2B, here they're talking about when the current location A1 is the last symbol. Okay, so it means that on the right hand side, there's nothing. U1 is nothing. U1 is empty. Okay, so what happened is for U2, it will be empty as well. Okay, that is what happened. Okay, so here just tell you the cases when B is for when the current location of the head is at the last symbol. Okay. What happened? Okay, and then what else? Um, okay. Oh, actually, I mean, when I talk about okay, so actually, do we have? Okay, we will see the example in the next slide. What does it mean? Okay, so here the first case is when we rewrite the symbol. The second case is when we move its head to the left. And then the third case possible that we can do to yield another configuration is to move the tape head one square to the right. Okay, similar idea to the second case, where for A is when we have symbols on both, we have symbols on the, what is it, on the left hand side and right hand side. Okay, so what happened is omega 2 must be equal to omega 1 and A1, so that when we move to the right, okay, A1 will just be added to the omega 2, and then the current location will move to A2 instead. Okay, so here the first case is talking about when you have the symbol on the right and uh, then just move it. That's it. Okay, but for the second case, 3b, we are talking about when the current symbol is the last symbol, and if you move to the right, basically you're moving to a blank cell. Okay, and that is what happens here in the 3b. And that's it. This is like five possible things that could possibly happen to the configuration to yield another. Okay, and here are some example. Okay, so for the first one, this is the kind of transition function you would have, is that from the state Q1 you may switch to another state, and you just replace the input with another symbol, switch from A to another symbol B, for example. And then the second case is when you have in one state and you see the current input, and then just move to the left. Okay, so here the first case is when you have symbol, the current location is not the last symbol, then you just move to the left. Okay, so here as you can see here from A, you just move to B. That's it. Move one location to the left. But here for 2B, this is the case where you see here the current location is at the blank cell after the last symbol. Okay, so what happened is that when you move to the left, then you need to remove this blank cell as well. Okay, we don't want this blank cell to be part of the content. Otherwise, we will have the problem that one configuration, that multiple configurations that are talking about the same situation, and we don't want that. Okay, and the same similar things go for the case 3, where we move to the right, move the tab head to the right location. Okay, for 3a, we just move it since there are items on the right. And for 3b, we are talking about when the current location is at the last symbol, and moving to the right, we're just moving to the blank cell. And that's it. Okay, so this is how the configuration works in the Turing machines. Now, with the configuration defined, now let's move on to define the accepting and rejecting, or the halting state. Okay, so here um, okay, so here we will define what is called the halted configuration if the current state is in edge, or in the halting state, basically. Okay, and we will call it halted configuration. Okay, and then the computation is basically a sequence of configuration where you can one can yield another within one step. Okay, and then we said the computation has length n if C1 yields Cn, and it basically means that from the first configuration, you need to go through n steps in order to get to the configuration Cn. Okay, and then the last one that you need to know about the configuration is that if we say the Turing machine M is set to halt on input string omega if and only if um, this configuration yields some halted configuration. Okay, so this is just to give you a formal definition of how this Turing machine will terminate, is that if it reach a halted configuration, basically. Okay, so that's it. Okay, and now let's look at the example. Let's say that we have this Turing machine. Okay, now we want to see how many steps does it takes to get this configuration to the halted configuration. Let's see. Okay, let's start. We start in this configuration. Oops, not that. We want the pen. Okay, we start from Q1 and we start from this M and then A. Okay, so here we're talking about first what happened Q1 C blank. What happened is we step to Q0, and now we move on to this. Okay, and then what else? We see Q0, we see A. Q0 and A. What happened? We go back to Q1, then blank blank A, and then isn't it the same thing? Isn't it? Okay, we just. Oh wait, is it the same as we saw earlier? I think it is. Okay, so I guess it's just the same thing, isn't it? It's just switching between these two rules, isn't it? Okay, so Q1 blank. Okay, then we just move to Q0 and move the location to the right. Okay, and then again. Uh, okay, let's just do it fast forward, I guess. Then we will just do the same thing, isn't it? This time we have like 3, and then we will do 4. Oops. Wait, how many of them are there? And then eventually 5. Oh my God, I'm running out of space. Okay. Okay, and then we should get to this point where we have a blank symbol here, and then with the here we will just go to Q0 where we have the blank 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 blank, isn't it? Okay, and here we just move to the. Oh wait, what is it? No, actually, my bad. Um, okay. For Q1. Oh wait, no, my bad. Okay, so Q1 when we see the blank. Okay. When we see the blank, we just move to the right. So that's why we move one more time to this location. And then with Q0 and blank, we move to the halt state and terminate. Terminate. Okay, let's just call it halt configuration. Okay, so how many times is it in total? So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, isn't it? I think it's 10 if my counting doesn't fail me. Okay, what should be it? Okay, 1, 2, 3, 4, 5, 6, 7. Okay, that should be it. Okay, so it should be like 10 steps, isn't it? Okay, so that's it. Okay, so this is how you count, like how many steps does it take to the halted configuration, how many steps that you need to take from one configuration to another. Okay, so that's it about the configurations. Okay, so any questions about the configuration? Okay, so now with the formal definition of the Turing machine is defined and also the configurations, now you should be able to see the whole thing about the Turing machines already. We have the complete Turing machines already. Okay, so okay, so now we have now you should have the basic grasp about the Turing machine of how it works, how we defined it, and also how it operates to compute the input string. Okay, so far we see that already. Okay, now the next part that we will look at, which we call it the combining machines. Okay, is that as you may notice is that this Turing machines is how would I say? You can think of it that it is some kind similar to like hmm, no, actually not similar to. No, actually, it's not similar to anything. Okay. What I want, what I want you to notice is that even the easy language, it is, it. I mean, it can be very complex when you describe it during using the Turing machine. Okay, that could possibly happen, and we will handle it just like how we do it in coding. When we have the complex code, what do? We break it down into pieces. Okay, we break it down into functions, break it down into different files, break it down into different classes, modules, whatever you call. Okay, but here in Turing machine, we just break it down into smaller machines. Okay, so but the principle is the same, that we want to break the code or the machines here down into the smaller pieces. Okay, and then we can just kind of say that if you got to this part, just go to look at the smaller machines that are I mean, we would look at this like this, where we have a big machine, break it down into smaller one, where each smaller one can how do you say that, can be described on its own. Okay, and that is what we are doing. Okay, and that is what the combining machines will do. Okay, and then let's see. Okay, so what this the smaller machines that I'm calling earlier. Okay, the official name is subroutines. Okay, it's just basically similar to what we call in the coding. Okay, so basically what we define as a subroutine of a Turing machine is a small set of states in the Turing machine such that it performs a small computation. Okay, so the idea is that the subroutine is basically a part of the Turing machines that try to perform some computation, and it can be on its own basically. Okay, and what else? And then usually we want our subroutine to have a single entry state and a single exit state, so it would be easy for us to track it. Okay, but however, this is not necessary. Okay, you can have the subroutine that have multiple entry state and multiple exit states. Okay, but that will make it difficult when you put together multiple routines together. Okay, what else? Okay, so here this is what I said earlier, that many complicated tasks, and then in Turing machine everything can get very complicated very quickly. Okay, so break it down into smaller subroutines is usually preferred and make it easier to track what is the Turing machine is trying to do. Okay, and here just to say that this subroutine give you like another point of view. We can see it as a hierarchical notation where um, uh, the the overall machine, or the overall machine, where the whole machine can be seen, can be rewritten as like a main steps, where the main step can be described by a smaller machine, for example. Okay, and here they say that hierarchical notation in the sense that the Turing machine as a whole can be seen as a complex machine that are built from smaller Turing machines. Okay, and then what else? Okay, so and then here we will start looking at this. So here is like, think of it like a library. Okay, so at some point in the Turing machine, when we design Turing machine, uh, we will come across some kind of operations that we want to perform multiple times. Okay, and it is just like when we do coding, when we see this kind of pattern, we just put this part of code in and put it in the library so that we can call it later when we need it. And the same ideas goes for the Turing machine. Okay, so this repertoire, uh, uh, the pattern, okay, we will put it. We just basically define it so that we can use it later when we need it, and we will call it basic machines. Okay, so basic machines are basically a Turing machine that the pattern of Turing machines that we see very often. Okay, and we will use it a lot. Okay, and then we will use this basic machine to build bigger machines, and even give us the rules for combining machines. Okay, so then and that's it's about the subroutines. Okay, so now let's move on to the basic machines. Okay, so here we will define some basic machines that we will see a lot. Okay, so what do they include? Okay, so here we will start from the very basic machine, which we will call it MA, where A here is just a symbol in the Turing machine. Okay, um, but here for this symbol, okay, it's not just alphabet. It's alphabet including the arrows, but this time we're not including the left hand symbol. Okay, and what this do is this. Okay, this Turing machine, or this basic machine, what it does is it just write symbol, the given symbol, into the tape. That's it. Okay, and that is why the left end symbol is not part of it, because we cannot just write the left end symbol into the tape. Okay, it's supposed to be only one left end symbol on the tape only. Okay, so we cannot write the left end symbol into the we will never be able to write the left hand symbol on the tape. It is there already at the beginning. Okay, what else? And then, but this one, in the case that this symbol is the arrow, either left or right arrow, it just means that it moved the tape to the left or right location. Okay, and that's it. And then halt. Okay, that is all this basic machine do. Okay, so there's a three variation that you may see of this basic machine. The first one is where you just do the writing machine, writing this symbol into the machine, into the tape, or you move the tape head to the left, or you move the tape head to the right, and then just halt or finish this basic machine basically. Okay, why do we need this? Okay, so hmm. Okay, so we define this because sometime when we have multiple state and we just want to write a symbol down. Okay, in the how do you say that? And in the case that you want to define it as a whole big machine, you may need to define this rule for writing this symbol for maybe even every possible state that maybe begin with. Okay, so that could make the transition function very big very quickly. Okay, so that's why we use the basic machine to avoid it, since we just want to write the symbol down whatever current state is. Okay, and then we just write it down and then move on. Okay, so this actually help us simplify the um the the transition function of the larger machine. Okay, and the same goes for moving to the left and to the right. Okay, and then later we will start using this basic machines to build a more complex one. Let's see. Okay, okay, so here to combine the machines, or basically or it can be the basic machines or even bigger machines. Okay, the idea of the how to combine them is this. Okay, individual machines, we can see them like we can think of it like a finite automaton. Okay, where the machines can be connected to each other when in the way that in the same way that the state of the finite automaton are connected together actually. Okay, but the idea of how to interpret this is different. The how we interpret this is this. Okay, when let's say that we put the connection like this. Let's say that we have three different Turing machines, M1, M2, and M3, and then we connect them like this. Okay, what does it mean? And then here we assume that we start from the M1 first. Okay, and what it means is this. The connection between the machine will not be pursued or be computed until this machine is halt. Okay, so first let's say that we start from machine 1. We will just running in machine 1 until it halts. Okay, if it never halts, then we just stuck here forever. Okay, we just keep running and process until the machine 1 halts, and then after it halts, we start looking at the current uh, input. Okay, after the M1 halts, what is the current input? If the current input is A, then we continue in the machine 2. But if the current input is B, then we will we will use the machine 3 instead. Okay, and then the same idea go repeat. Okay, where we just keep process the input using the if it was A, then we just use M2 to process the remaining string. Okay, and then we see that if it halts or not, and so on. Okay, and if there are other connections, we just keep moving and keep going and so on. Okay, so basically, think of I mean, you can think of the Turing machine as like a giant, a big state or something like that. Okay, where inside of it like is like another machine inside. Okay, so you need to process it first before you can move to another, and that is the idea. Okay, so there you go. Okay, so we just work until M1 halt. Then if the current symbol is A, then we use the M2. If the current symbol is B, then we use M3. That's it. Okay, so here are the example. Okay, that and here just to show you that the big machine can be, I mean, we can actually describe the Turing machine as just one machine rather than a combination of smaller machines. Okay, we can still be able to define one big Turing machine. Okay, but it is much more difficult and difficult to understand and difficult to follow. Okay, so that is why we prefer to break it down into smaller pieces. Okay, so here this slide just to show you that you can actually combine them together and build a big, one big Turing machine. Okay, so here they assume that we have three machines, just like in the previous example, M1, M2, and M3. Okay, and then for the sake of ease, for make it easier to prove this, easier to show this, we assume that the states of the three machines are different, are totally disjoint. Okay, the set of states are disjoint. Okay, so basically there's no same state in different machines. Okay, and with that, then we can, if we want to combine these three machines together, we can create a machine M that basically the set of state is the union of all of them. And then, uh, okay, so here we assume that we are trying to build this machine. Then our start state would be from the S1, from the machine 1. And then the halt state would be from the H2 and H3, okay, together. So union of them. And then what else? And then the only thing left that we need to define is the transition function. Okay, so the alphabet is the same for all these four machines. Okay, for the transition function, this is what happens. Okay, so here we're talking about what is this? Okay, so here we are talking about the K1. Okay, we are talking about the K1 state, we just copy from the M1 machine. For the K2, we just copy from the M2, and K3 just copy from the M3. And then last one is here we add the connection between the different machines in the it is in the last bullet point here. Okay, so here we talk about if Q is in H1 or halting state of machine 1, then we need to check that um, if the input is A, then we just move to the machine 2, where we start at S2. And if the current input is B, then we just move to the machine 3, starting at the S3 state. And that's it. Okay, and here, and that's it. This is how we, I mean, um, if you just build one big machine, this is what it will look like. Okay, so, and if you just break it down into the smaller machine, this is what it will look like. So you should see the difference that is, and this way is much easier to understand compared to this. Okay, and what else? Okay, and that is pretty much it about how you combine the machines. Okay, so now we will start looking at some basic, some machines that are a simple one that are used often. Okay, so here are some others basic machines. Okay, that you should know. Okay, and there are other basic machines as well that you can look at in the textbook in this examples. Okay, there are other basic machines that you should know about. Okay, so but here in this lecture we will look at two of them. Okay, and which we call it L blank and R blank. What is it? Okay, the basic machine L blank, what it's trying to do is this. It's trying to find the first blank square to the left of the current head tab. Okay, where to the left of the current location of the tape head. And the same idea go for R blank is to find the first blank square to the right of the current location of the tape head. That's it. Okay, so how could we achieve that? Okay, so this is what it looked like. Okay, this is R blank and L blank like this. Okay, so what does this symbol means? Okay, so here, okay, oh, what is it? Oh, okay, so here, okay, here, just one more comment about this, about the basic machine. If we move the head to the left for one square, sometimes we just use L. Okay, letter L, big L for moving to the left, and letter big R for the basic machine for moving the tape head to the right. And even for the letter, sometimes we just write down a letter to show that this is a writing machine to the left, to the current location. Okay. So, okay, but this is different from here. Okay, this is the machine. Okay, so this symbol must appear at the node, not the transition. Okay, so don't get confused between this as a writing machine compared to this, which is just to check for the symbol. Okay, I mean, this is just for the check the symbol to either move to this machine or move to this machine. Okay, so this is a rule in transition function. Okay, don't get confused between these two. Okay, back to this. Okay, so here this symbol just means that start from this state. Okay, start from this state. Okay, same for here. Okay, so start from this state, you just move. Let's start from the right blank. Okay, what it does is that first, at the beginning, it just moved to the right. Okay, since we just want to find the first blank on the right, so we need to move to the right first. So first we need move to the right, and then what else? Then we check this. Okay, we check that is it a non-blank non-blank symbol or not. If it is non-blank, we just keep moving to the right. That's it. Okay, that's why this arrow to itself just show you the self transition where the condition is non-blank symbol. Okay, this is the transition. Okay, so as long as we see a non-blank symbol, we just keep moving to the right. Okay, and as you can guess, it will end when you see the blank symbol, and it will just stop and terminates. Okay, and that is how it works. Okay, and what else? And the same ideas go for here. Okay. Oh, actually, you can think of it like this, where this one actually, you can think of it that it has another transition. If you see blank, it just go to the halt state. The same go for L. Okay, it basically will halt as soon as it see a blank symbol. Okay, but we ignore this because basically this transition will connect it to the next machine. Okay, it will not. You can replace the halt the halt state with the next machine that this one is attached to. Okay, so that is the idea. Okay, so this is what the right blank and R and L blank do. Okay, and for this one just show you that sometimes you want to repeat the whole the you want to repeat the same machine multiple times. We can use the power, okay, to indicate that power two to say that it repeated twice. If it repeat three times, then to the power three and so on, something like this. Okay, and what else? Oh, okay. So, and this one, okay, this one just to define the non-blank symbol. What does it mean? Okay, it just means that non-blank symbol is just it just means that every symbol that is not equal to the blank, basically. Okay, that is what it say here. Okay, so these two are the same thing. Okay, what we here we use the bar to show that it's like a complement. Okay, and say that this is non-blank symbol, something like this. Okay, and that's it. Okay, so here are some basic machines that you should know. There are others in the textbook as well that you should have a look at. Okay, and that's it. Okay, so that's it for today's lecture. So in this lecture, we look at the introduction to the Turing machine. We look at the definition. We look at the configuration which help us define when the machine will stop and terminate, or when it will accept or reject a string. And then finally, we look at the combining machines to see how the Turing machines can be described by breaking it down to smaller ones so that it can be described easier. Okay, so that covered the basic about the Turing machines. Okay, the next next lectures, we'll start looking at more the different variations of the Turing machines and also different things that we can do to it. Okay, so that's it for today. Any questions? Okay, so if there are no questions, then I will let you do the quiz then. Okay, so again, today quiz, two things that two homeworks that you need to do. First is quiz that you need to finish it by 12 p.m. today, and another one is the problem set that you need to finish it by next Thursday. Okay, so what else? Okay, so now you should be able to see the quiz. Okay. Okay, so don't forget to do both homeworks. Okay, the quiz by today at 12 p.m. and the problem set by next Thursday. Okay, and for the video lecture, I normally post it on the if you look in the Google Classroom. Okay, you will see in something like this. Okay, week 9 slide video lecture, something like this. I have put it um, all this all this every week. I already put it there so far. Okay, and the same I will do the same for this week as well, and we continue to do this uh, until the course finish. Okay, so you can check it. You can check it later if you want to revise it. You can check this lecture video. Okay, so if is there any question? If not, then that's it. Okay, so see you next week then. That's it for today. Okay, so see you next week. Don't forget to do the quiz and the problem set. Okay, and that's it for today. See you next week. Bye.